Okay.
Thank you.
Yeah.
Okay.
Okay. So I'd like to thank, first of all, I'd like to thank Dr. Mao and Dr. Hu for being on this committee. I'm glad you guys both could be here. Uh, so let's start. My name is Alexander McMoil, and today my topic is a multi-channel functional electrical stimulation device with closed-loop feedback using magnetic hand tracking. So we'll be focusing on electrical stimulation of the hand. Um, to start with, functional electrical stimulation, or FES, is a common therapeutic tool that involves sending electrical signals through the skin into the motor neurons to contract a targeted muscle. Um, Conventional FES is expensive, not portable, and utilize a limited number of channels. Additionally, they're traditionally open loop schemes, so they cannot dynamically adjust the parameters to the state of the hand, which raises problems when the goal of FES is to achieve a targeted hand pose through the contraction of specific muscles. And so to accomplish this, uh, we, we we have three contributions. The first is a multi-channel functional electrical stimulation device. The second is a magnetic hand tracker to get the feedback. And finally, we'll look at how to combine these systems in closed loop control with two contributions, parameter searching and the therapeutic loop. And so we'll move on to the functional electrical stimulation. To note, I'll be discussing the full device. However, I did not design the hardware. My advisor, Dr. Guangyang, designed it. I'll just be discussing the I'll just be discussing it for um, co completionist sake, let's say. And so a little bit of background on FES. FES is commonly sent out as these biphasic square waves, as you see on the right. We have a leading pulse, an interface interval, and the lagging pulse, as well as an amplitude and a pulse width. And these are sent out at a constant frequency. And so a therapist would usually place an active and a reference electrode on the muscle that they intend to contract. For the hand, this is on the dorsal side of the forearm to achieve extension of the hand. These FES devices are current controlled, so they require a high compliance voltage due to the varying conditions of the skin impedance. Here is a overview of the hardware. You'll see that the microcontroller on the bottom is the brains of the operation. It handles the timing of the signals, which are sent to the waveform synthesizer, um, which convert the individual signals to this biphasic square wave, which is then sent to the VCCA, or voltage controlled current amplifier, which takes this biphasic square wave and amplifies it to a current controlled square wave, which is then sent to the demultiplexer, so we can split it up into 8 different channels. And all of that is powered by a 12 volt power supply. And so we'll start. We'll look a bit more into the waveform synthesizer. You'll see in the top left, the microcontroller sends out two signals, a leading impulse and a following impulse. And depending um, on the timing of it, it will um, as a digital signal. And so it will also send out the analog signal as well, which controls how the 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 amplitude of the uh, analog leading and analog following impulse, as you can see on the right. And so that goes into that goes to the bottom left figure, which transforms these the two separate analog leading and following or lagging impulses, and converts that into the balanced biphasic waveform. And so you'll see on the right is how we is the conversion of that. So if the leading impulse is high and the following impulse is low, then it's going to convert it into a high voltage. As you can see the 10 volts here, and vice versa. It's going to convert to the negative impulse. And so our system is capable of producing both these anodic leading, which is where it's positive first, and also cathodic leading, where the voltage is negative first. After that, it's sent over to the voltage-controlled current amplifier. On the left, you'll see in the blue circle is a low voltage to current converter, and then you'll see a pair of high voltage scaled current mirrors. On the right, you'll see the demultiplexer, which which converts this signal, which splits up the signal into 8 different channels. So we have one single line of one signal, and that gets demultiplexed into 8 different channels. You'll see the demultiplexer here on the left, the channel selection address, and then we use optical transit. Optical. So I can't think of the word right now, but we split that. We use transistors to split that to handle the high voltage necessary for the device. And here's just a validation of the system. You'll see at the top is the single signal that comes out of the VCCA, and then each one of these is a separate channel. And here is a picture of our prototype. You'll see on the top is PCB1, which contains the pulse generator and the demultiplexer. And on the bottom is PCB2, which contains the waveform synthesizer and the voltage and the VCCA. Okay. Next up, we'll talk about the firmware. I'm just going to go through an architectural diagram of it. We start by initializing the serial communication and the ports. Following that, we enter a loop, the operational loop, which checks for serial communication. And if there is parameters in the serial port, they're sent via the scheme here with the frequency, lagging, leading amplitude, pulse width, and channel number. Notice that we didn't specify a lagging pulse width. That's because we use the lagging pulse width to automatically charge balance the wave according to the equation below. And so with all these parameters, we schedule a time for that pulse of that channel to be sent out, which is the time of next pulse for this channel. And this was inspired by real-time operating systems, where in the loop we continuously check each channel, and if there is a channel, then we set the flag of pulse ready to true. And if there are multiple pulses that are ready to be sent out. We send out the one with the earliest scheduled pulse. And so with the and once we have a pulse that's ready, uh, we reset the necessary flags, and then we send out the pulse, which is just a very tightly scheduled um, timings where we set the address bit and then the amplitude, and then according to the waveform synthesizer, we set the leading pin high, and then go through the rest of this, which you'll be able to see in my thesis. Um, and so that's the entirety of the firmware done. We also have a second version which implements multiple grounds. So by implementing a demultiplexer for the grounds, we can increase the combinations of signal reference electro pair combinations, which we utilize later when we in the optimal electro placement section. And this requires very minimal changes in the firmware. We just add a few more parameters, such as the signal and reference addresses, and we just send the reference address in the pulse as well. And in the figure below, you'll see the general scheme of how we plan to implement this electrode searching. So you'll see we have this represents the back of the forearm, and we have the ground electrodes running through the middle of the forearm, and then active electrodes on either side. Now that we've finished that, we can go to the evaluation. So this one represents the characteristics of the FES curve. You'll see we have a less than 10 microsecond rising and fall time, and a 0.8 milliamp resolution. Here we validate, we see that all 8 channels are operating simultaneously, with the bottom one being one selected channel. Here is a validation of the asymmetric waveform. You'll see the top is symmetric, whereas the bottom is asymmetric. It has half double the pulse width and half the amplitude in the lagging pulse. Here we show a variety of frequencies, amplitudes, and pulse widths operating simultaneously with all symmetric waves. And then the following image is very much the same, but with asymmetric pulses. Okay. Moving on to the magnetic hand tracking. Once again, the hardware design is done by my advisor, Dr. Guangyang. A little bit more background on hand tracking. Hand tracking is a very well-studied field. Utilizing magnetic fields to locate the pose of the hand has some advantages compared to other approaches. Visual approaches suffer from occlusion. IMU-based approaches suffer from drift, and EMGs only work on healthy hands. You'll see in the top right you'll see how magnetic hand tracking is generally approached. We have transmitter coils on each of the fingers in figure A, and then figure B shows how the transmitter coils transmit a magnetic flux, a magnetic field, and the receiver coils will be able to receive the magnitude of these magnetic field, as you see in C, as you see in figure C. And velocity in figure D, you'll see that we will be able to differentiate the different magnetic signals from the opening and closing of the hand. And then below is the equation for determining the position of the hand, or determining the magnetic field from the position of the hand I believe P. And you'll see that the inverse problem of determining the position of the hand, or determining the position of the transmitter rather, from the magnetic field is a much harder inverse formulation. Here's a brief overview of the hardware. You'll see at the top are the receivers, where the receiver goes into where the receiver takes in the magnetic field and goes through an amplifier, precision rectifier, and then a low pass filter, which is then sampled by the MC by the microcontroller. And the microcontroller also addresses the transmitters via TD time division multiple access scheduling um, through a multiplexer, which then goes into the oscillators, and finally to the transmitters. And then all of the data is sent to a central computer, um, the converting the magnetic signals into the angles, which we use neural networks for, and we'll get to that in a second. But here is our prototype. You'll see the transmitting coils are on the intermediate phalange of each finger, as well as on the main box on the forearm. And the receiver coils we have 4 receiver coils on the dorsal side of the palm, with 2 in the front, 1 on top and 1 on the right, which we found has the highest fidelity in tracking. The receiver coil on the right helps tracking of the thumb greatly. And so, like I said before, we use neural networks to determine the position of the hands, the pose of the hand from the magnetic fields, from the 4 magnetic fields. And so, why do we use neural networks? So, for one, the voltages are from the hardware are highly nonlinear, as you see in the figure on the right. These signals will flat bottom out at the bottom. Traditional approaches use forward iteration based on common filters, which are usually computationally expensive. Whereas neural networks, once trained, are like computationally bounded. They require a set number of computations each time. And so, moving on, we discuss how we want to model the hand, which plays a great role in deciding the structure of our neural network. So the hand is made up of about 27 degrees of freedom. You'll see in the figure on the right, I label all the joints and the bones of the hand. And we want to be able to simplify the hand, simplify the number of the hands such that we reduce the degrees of freedom that we are recording. And to do this, we focus mainly on the flexion and extension of the hand. So we simplify the wrist into which usually has 2 degrees of freedom, flexion and extension, and ulnar deviation, and we only track flexion and extension. For the non-thumb fingers, we track the MCP or metacarpal phalangeal joint, the PIP and the DIP, with the flexion and extension of those joints as well. For the thumb, we track the abduction/adduction of the trapezial metacarpal or TM joint, and the flexion and extension of the MCP and IP joints. And so that gives us about 16 degrees of freedom to work with. However, we can simplify it even further. We use biomechanically locks or constraints of the DIP joint and the PIP joint to simplify even further, such that we only need to track the PIP joint of the non-thumb fingers and the MCP joints of the thumb to obtain the full pose of the hand. And so we end up only needing 11 degrees of freedom to fully model the hand. And so that leads us into the design of the neural network. We utilize 6 separate neural networks, one for each finger, and then also an additional one for the wrist. Each of these networks has 4 input neurons, which corresponds to the receiver coils of the that are received during the transmitting of the node, as well as 3 hidden layers with 200 neurons each, as well with reboot activation functions. During training, we used a leap motion controller to obtain the ground truth of the angles of the joints. We train it in 3 sessions. We utilize 1 minute for the thumb, 1 minute for the non-thumb fingers, and 20 seconds for the wrist at about 30 hertz. So 1800 samples for the first 2 and 600 samples for the wrist. We split the data set into the training, validation, and testing set, and we use an atom optimizer for yeah. Okay. Finally, we get to the evaluation of the system. Here we see the tracking performance for the index finger. At the top is the MCP joint, and the bottom is the PIP joint angles during a flexion cycle. So the hand starts at full extension, it moves to flexion and back to extension over the course of about 5 seconds. Here we see the evaluation for the thumb during for the the TM joint during adduction, abduction, and B, the MCP joint during flexion and extension. And you'll see that it matches quite closely to the ground truth. Additionally, we also have the tracking performance of the wrist during extension, during this extension, flexion, extension sequence over the course of about 18 minutes. And you'll see this tracks very closely to the wrist. And we notice that additionally, the slower you perform the motions, the higher the accurate, the higher the lower the error. So here is the quantitative results for our data. You'll see that most of the most of the slow most of the error for the slow and even medium is less than 5 or 6 degrees, whereas fast, which is under 1 second, tends to get much higher error. And so I have a video demonstration of the system working here. You'll see the thumb during these flexion extension motions. You'll see it tracks quite accurately. And here's the thumb individually tracking. and here's each finger flexing and extending individually. And also here's me showing that the wrist is working. Okay. And now we are combining these two separate systems into a single one with closed loop control. And we have two main contributions to this, which is searching for optimal parameters and also implementing this in a therapy session using like a therapeutic loop. The overall system looks like this, where we have the computer controlling the state the timing of everything, in which it sends out FES parameters to the FES device, which sends out the electrical pulses to the hand, which determines the pose of the hand, which the magnetic hand tracking, will then collect the magnetic values for, which was then sent to the computer to convert that into the angles and determine what the FES parameters should look like, etc. And so in the therapeutic loop, and so overall, what a therapy session would look like is that we would train the hand tracking models on a healthy model on the healthy hand. Then we would place the hand tracking and the FES device on the impaired hand, and then we would perform parameter searching of optimal electrode placement and tuning the frequency. And finally, we would move into the therapeutic session. And so with the parameter searching, like I mentioned before, in the FES section, we use a multi-ground device to search out different signal reference electrode pairs. And so we have a two-stage search. We have an initial search in which we rapidly cycle through combinations of the active and the reference electrodes. And we record the combinations with the most extension of the hand. And so this is to determine which electrodes, which pairs are on the motor neurons. And so after that, once we determine which pairs are on the motor neurons, we then hold these pairs for longer to determine which combination has the greatest extension, and that's the one which will achieve the most. That's the one that will achieve that will perform the best. Secondly, we also implement a frequency tuning algorithm, in which we maintain a constant pulse width and amplitude, and we ramp the frequency until there's no change in the extension, which we determine is like less than a half a degree change over a 10 hertz window. In the therapeutic loop, we use a finite state machine to determine which phase it is at. First, we have an initial ramp over 5 seconds, which smoothly ramps the amplitude to a desired amplitude. 5 seconds is generally what paretic hands should be ramped to, as we want to avoid like a rapid contraction of the flexion muscles. After that, we wait a couple seconds to see if the hand is at the desired extension. And then if it's not, we implement an adaptive kick in which we continue ramping the amplitude. And then once it's at the desired extension, we stretch. We hold that parameters for 5 seconds, and then we ramp down again for 5 seconds, and we rest again for 5 seconds or for 10 seconds, which should be about double the length of the stretch. And so here we evaluate the frequency tuning. You'll see the wrist extension is in blue. Uh, and the optimal frequency for this testing was at 28 hertz, the vertical line, right at the beginning of where it starts to plateau. And here's the evaluation of the therapeutic loop. You'll see each phase is labeled, where um, the first repetition is done to determine the extension threshold, and after that we can enable the kick um, to sort of kick it into that extent to that desired extension. So in conclusion, we had three contributions. We developed a portable, inexpensive, multi-channel, programmable, functional electrical stimulation device. We developed a magnetic hand tracking system based on neural networks using time division, multiple access scheduling. And we combined both these systems to create a closed loop FES device to find optimal parameters and run automated therapy sessions with closed loop control. In the future, we'd like to test the closed loop control on impaired patients and determine the correct better timings as well as more comfortable ramping for patients. One to extend the closed loop control to include rather than just the wrist for these evaluations. We want to be able to include all the fingers to take advantage of our magnetic hand tracking and get a more complete picture of the extension of the hand. And then additionally, we want to further develop the optimal electrode placement algorithm, as that has not been even validated yet, as the hardware is still in progress. The FES here are the publications for the FES and the hand tracking plan to be submitted to medical engineering and physics and IEEE transactions on instrumentations and measurements. Thank you. Any questions?
Okay, thank Alex for the presentation. Now we can have some questions, right? So let's start from Professor Hu. Do you have any question?
Sure, yeah. So this is a very interesting work. So from my understanding, you have six different neural networks trying to predict the gesture of the hand. Is that correct?
Yes.
So um, how large is the so you have a three hidden layer with 200 neurons.
Yes.
How powerful is your microcontroller and what is the latency of this? Does the I guess my main concern is does the latency affect the control loop?
Um, so first of all, the latency does not control does not affect the control.
Okay.
We have we currently run the control on about 20 milliseconds, like each 20 milliseconds window, in which is um, the latest the magnetic hand tracker can update the magnets for each finger. So we use about 4 milliseconds for each to measure each transmitter. So that's 4 times 6, so 24 milliseconds to completely run through each of the all six of the transmitters and get a complete picture of the system.
Yeah, I
Uh,
think Alex,
and
that's supposed to be 12, right? 12 millisecond.
I'm currently using a little bit a slow run just because I found there was a little too much magnetic crosstalk on 2 milliseconds.
Okay.
Um, and also to address the neural network, currently we're running the neural network on a computer. We have two separate microcontrollers for the FES and the hand tracking. and the computer talks to both of them, and then and also does the inference for the machine learning. I think it takes about 1.5 milliseconds to run the inference in totality. Uh,
Okay. Um, then the so in your training data set
mhm,
for this, um, I'm just curious, like, did you try the generalization capability of your data? You have
mhm,
um so this did you try, like, for example, using a different hand model
mhm.
and see how accurate that is? Either it be like, oh, does this overfitting, I guess? And
Um,
yeah.
yeah, I understand what you mean. It doesn't work. It doesn't work well with different hand models. We've tested it on three subjects, and generally I've tried testing the different data sets on someone else on other people's hand, and it performs much worse. I think that's mainly due to the differences in hand hand structure, changing the how the receivers uh, the information that the receivers get. I think if I were to change, I think I would like to. I think generalizations is definitely a goal in the future.
Okay.
Um, where we could where especially if we get more uh, data from different people with different size hands, we could definitely. I think generalization is definitely much more feasible with more models.
Okay. So
Yeah,
the
usually
general,
for each user, you need to train before he
Yeah.
can use.
Mhm.
I see.
So that is the best way, right? Because different people will have different size of a hand. So the training is only is like a user specific.
Right.
If you use rare another person's hand, then the tracking becomes not accurate anymore. Yeah. This is
Um,
the main downside of this approach. It's like you
right.
have to be trained like individually.
Right. I think this is a problem for like almost all the similar approach. It's not like a unique challenge. I think like they are probably like works trying to do automatic calibration
Yeah,
for
yeah,
the
yeah. Even
and
for the iteration approach, forward approach, you still need the size of the hand to do the model, right? So this is a common
exactly.
problem. Yeah.
Okay. So
Mhm.
but I think that's something that's probably like worth exploring
Mhm.
down the road. And then I have another question. So, from my understanding, you this is automatic closed loop. So you are looking at the neural network is basically predicting, the hand movement, right? See if it's fully stretched or if it's moving. Is that correct?
Yeah, the neural network it's I think it simply just predicts or it's neural network just performs inference to determine the angle of the hand the pose of the hand, the
Right,
current pose
right.
of the hand.
Right, the pose of the hand. So, the are you the data you collected? Is this from like a patient or like from a healthy
This
person?
is this is from a healthy hand. This is from I collected it myself.
Okay, but then like the problem is that the healthy hand and with the
Yeah.
people with it's not the same, right?
Yeah, exactly.
The muscles probably like they are different. There
Yeah.
are probably like contracture,
Yeah, yeah.
right? So that all affects the accuracy, and
Yeah.
also I think one thing that you need to bear in mind is that like what is the safety bound? Like if, for example,
Mm,
like my hand like it's already very hard to stretch, for example,
yeah.
right? But you are keep increasing the pulse, the stimulation. Does that might hurt my hand, right? Because you are pushing very
Yeah.
hard, but that's my limit because of my issue.
Yeah, so again, like I said, in future work, we really want to test this on impaired patients. Um, that's what I intended the frequency tuning to be, where the frequency tuning sort of does one test where it goes beyond sort of like what they should be, and then when it like, sort of like plateaus out, we sort of like dial it back down.
Very
Um,
good, but very good. But also, like one thing you need to keep in mind, like when you move too many times, your muscle might start to get tired.
mhm.
So,
Yeah,
so the limit is also changing, right, during the
yeah.
a period of time. Did you, was that like considered in the design? Um, so
So I
so that
think
Mhm.
yeah, our I guess intended use case would be we wanted to be able to achieve the mat basically the same stretch each time.
Mhm.
Um, I think
But
you do
like
bring up a good point with the stretching with the sort of maximum extension changing over time. Um, I think I think there've been some studies on this where they utilize like SEMG and um force force sensors to determine like how much force is being applied and sort of trying to achieve the same force each time. Um, I think for our case, we simply wanted the hand to get to the same position. I think um, Mike has a little bit more details on the bio the biological side of that.
Dr. Lee,
Um,
can I follow up on Dr. Who's question just
Yeah, yeah,
to
go
kind of
ahead. Go ahead, Mike.
pull this all
Please.
together? So, Alex, nice job. And I know that most of this is really focused on the electronic architecture, but in terms
mm,
of kind of the motivation for why we developed the system, there's a ton of FES systems out there, and there's this idea that we can do closed loop. But what is really kind of the focus from a therapeutic standpoint when we think about integrating the closed loop, right? Is it the idea of just being able to passively stimulate somebody? Or is it the idea that we want to kind of leverage what they can do and then be able to provide the supplement to get them to the full hand opening,
mm,
right? That's the part that I think when you talk about this, you want to make sure that you emphasize because, again, passive stimulation isn't going to lead to any type of adaptive neuroplasticity, right? There has to
yeah.
be voluntary movement that occurs. And so the idea here for the closed loop system is that we have the stimulation available to supplement what the person can do. And what we see in a lot of cases, and this is just inherent in a very heterogeneous population like stroke, is that there's people that, like Dr. Who said, there's contractures that have very little movement. There's people that have, kind of mild deficits. There's people that have, almost negligible deficits. But what we want to try to do is get people to leverage what they can do, and then the stimulation comes in as a supplement. And so that's really the whole idea of this closed loop scheme. And that's what differentiates it from a lot of the other systems that are out there. In the case of EMG, that's fraught with all sorts of limitations. And that's the reason why we got into this idea of magnetic tracking. Yeah, so that with this therapeutic loop, Alex, I think that's really what the focus needs to be on is that
Yeah,
you go through this cycle, right? But the focus is not to just basically kind of just go through this
yeah,
as a matter of routine. It's to basically tell the person you do it, and then
yeah.
when they're not able to get to a certain past a certain point, that's when the stimulation kicks in and
Mm.
supplements the movement capabilities.
Yeah, I believe I mentioned that in the paper where before the initial ramp, the patients are like prompted to attempt to extend their hands as much as they can. I sorry, I forgot to put it into the presentation, but like a few seconds I think at the start of the ramp, they're prompted to attempt to extend their hand to build that neuroplasticity, as Mike was saying.
So I think I understand that part. I guess my question is that like we don't want the stimulation to overstretch
Yeah.
like the limit, the physical limit, and that hurts the patient, right? We don't want that to happen.
Yeah,
Right.
that's the safety concern, right?
Right. The safety
Yeah.
concern.
Mm.
That's and that's pretty much that's a pretty valid concern, right?
Yeah.
Yeah.
Yeah. So okay. So that's that.
Yeah.
So that's why, just like Mark said, so the passive stimulation doesn't work. So the patient needed to actively move their hand. The FES only provides supplemental
I see.
work to let the patient reach the goal of the hand, right? If they don't feel comfortable for the stretching of the additional stretching, probably we need to limit the motion of the hand as a target, right? So we need some adjustment for the eventual goal, right? To make them in the comfortable zone of the
Yep.
stimulation. So
That
passive stimulation doesn't work at all, I think. You need to have the patient actively involved to the hand,
I
to move
see.
the hand. And then you additionally provide stimulation
I see.
to let the patient, the hand to move to the target.
I
Yeah.
see.
So to your point, Doctor Who, it's the idea that we have the kinematics to be able to tell us where they are in space, and so
Mhm.
that prevents it from going too far for from causing any type of harm, right?
Mhm.
The bigger concern, to your point, is more about like kind of the focal discomfort on the at the point of stimulation, right? Are we causing any type of burning or anything like that by just trying to get to that kind of desired endpoint? But as far as kind of overstretching them, that's not a concern because that's the whole premise of the device is basically
I
to be
see.
able to monitor what they're doing in real time, so that
Yeah,
way we can adjust the stimulation.
I see.
Yeah, that
So,
actually avoid overstretch, right?
Yeah.
Because we have a hand tracking device. If you have overstretch, then it will reduce the stimulation level. Yeah.
mm. So that comes back, I guess that then like that comes back like how accurate the estimation would be, right? Even without considering the generalization, you are going to retrain this for every patient. Um, using healthy data is not a good idea, right? So you and even with the let's say like the patient's data to retrain to retune the model to estimate this. I'm not sure like if there are other factors that might affect the accuracy of the model. That could be a concern because if you are not estimating the postures correctly, then the control is going to be off as well, right? So, Alex, I guess my question is, how accurate is your estimation right now for with the patient's uh, not healthy data?
Yeah, we don't have
Yeah.
any
Yeah.
data on the patient yet.
I see.
Yeah,
Yeah.
most of data on the healthy side.
Okay.
Yeah,
No,
right.
I think
Because
overall,
if you work on the patient, you need the IRB approval,
sure.
all kind of stuff. I think
Sure.
Mike's lab has a patient we can work on, but we are not allowed to do that because we don't have IRB approval
Mhm.
to
Sure.
test that device yet. Yeah.
Sure. Yeah, no, I think overall it's a really interesting work. I just think the safety concern, well, the accuracy which leads to the safety concern, really need to be investigated when you are actually doing the testing, right? The design and testing. That's my main comment. But overall, the whole system design, the whole idea, I think it's a really interesting idea.
Mm.
Um, so. So so Alex, is it like like we have other, for example, we have other 3D cameras, right? Like the Microsoft Kinetics that give you
Yeah.
like quite accurate like a 3D, or even other cameras give you this. So is your design mainly because it's lightweight, portable? Are that's main feature of your design compared with like a really accurate 3D camera?
Yeah, that too. And also like it's also it's also relatively inexpensive.
Okay.
Like the FES device cost like about $30 compared to like some of the other ones which cost like
I
a
think
thousand,
Professor
two
Hu is
thousand.
asking for the hand tracking,
Yeah,
optical
Yes.
approach, right? Optical
Right. Right.
yeah.
delivery
Right.
is the
Um,
mainstream.
I
So
believe
why
for
are
the
you go for the magnetic tracking?
yeah, I believe for the optical approach, um, the main concern with optical approach was that especially with the collision with you mentioned with the hands, I didn't first of all I didn't have access to a like very good hand recognition, like a 3D hand recognition camera. Uh, but
No, our leap
and
motion controller can do that.
yeah, yeah, the Wii Motion is relatively good at that. However, it did tend to, especially when they couldn't recognize the palm. A lot of these are palm dependent or do like palm recognition. They fail, especially like with when the fist is closed, or when the wrist is in a certain position. And especially with like Prodic hands, these their hands tend to be in um their hands tend to be in much like not conventional poses, which I don't have any I also don't have any data to back this up, but I think 3D cameras would have a harder time tracking a Prodic hand than as well than a healthy hand.
Okay.
Um, yeah. Let's see. Um, yeah, I think especially with actually I have an image here. So like just with like common forms of spasticity, we have like the flex wrist, the flex fingers, thumb and palm, clenched fist. Um, some of these are would be I think are I would believe would be difficult for the for a hand tracker to assess. But again, that's just the only 3D camera I've had access to is Delete Motion, and from what I've seen, the poses similar to these common forms of spasticity, it didn't perform well with these. So I'm just kind of generalizing that to everyone, but I'm not sure if that's entirely correct.
Okay. Okay.
Yeah. Okay.
Okay. Yeah. That's all my question. I think it's a really interesting work.
Thank you.
Okay. Thank you, Professor Hu.
Yeah.
So Professor Mo, do you have some
Yeah,
question?
okay. Alex, excellent job. I'm very
Thank you.
impressed. You did in terms of quality and also the amount of work I can see. Um, Congratulations. I have only one
Thank you.
question, which is so when you do the stimulation,
Mhm.
why do you use a biphasic signal?
Yeah, so with a biphasic signal, we want to balance the charge of the signal so that the charge doesn't accumulate on the skin.
Okay, great.
Um, yeah.
Yeah, thank you. I'm done. Yeah.
Okay.
Oh,
Okay.
thank you, Professor
Thank
Mo.
you.
Uh, Mike, do you have any question for the? You know most of Alex's job, but if you have any question
No,
for him,
it was a good job, Alex. I think,
Thank you.
again, we've come a long way with this
Yeah.
from, kind of just conceptualizing it and then being able to like kind of develop each constituent part and then bring it
Mhm.
together as an entire system. It's been a long road, and I think that you've done a great job with that. So I'm quite satisfied, and I think that the one thing to not lose sight of, because I know your specialty is just to kind of think about how does this system kind of fit in the ecosystem with all the others out there, right?
Yeah.
And there's something that's unique here, and that's what I want to make sure that you have as a selling point when you go on to the next step in your career.
Yeah. Thank you.
okay.
Any last words, Doctor, going on?
Okay. Then Alex, you may need to excuse us. You need to leave the meeting. So the committee will have some discussion,
Yeah.
and then we are ready, or I will text you so you can come back.
Could you please stop recording first?
Yeah.
Okay.
Mm.